Welcome. In this video, we cover section 3.4, Boolean Algebra. Two big ideas. One is the logic set parallel, and then two, Boolean Algebra itself. What is Boolean Algebra? Let's begin. 1. The logic set parallel. There is a parallel between logical statements and set statements. For example, De Morgan's laws. We have De Morgan's laws in sets, and we have De Morgan's laws in logic. In logic, it says not P and Q is equivalent to not P or not Q. It's sort of like a distributive property for the negation, and the and turns into an or. Something similar in sets. The complement of A intersect B is A complement union B complement. I can distribute the complement so long as the intersection is turned into a union. And there are many more parallels. All of these, look at this. So that big set of properties that we studied with sets, that's on the bottom, every one of those has its parallel in logic up above. In fact, take a few minutes now, pause the video if you'd like, let your eyes sort of wander over this table, and think about how do you convert from one to the other? What are intersections and unions in sets equivalent to up in logic? So take some time and think about that. When you think you've got some ideas about how that correspondence works, let's consider this sort of tactic. Making the following changes turns a logical statement into a set statement. So here's the dictionary. It says if you see PQR in logic, that's like symbols ABC in sets. And is like the intersection, or is like the union, negation is like complement. In logic, we might say equivalent, but in sets, it's just equality. We didn't talk about this so much in logic, but T is tautology, is always true. That's like the universal set. C is complement, that's like always false, and that corresponds to the empty set. So if we make these changes, we get all the statements in one table converted into the statements in the other table. Try this. Convert the top logical expression into an expression about sets, and convert the bottom set expression into a statement about logic. All right, take a minute or two and give it your best try. Go to it. All right, the solutions. On top, that is the solution, and on bottom, that is the solution. I hope you gave it a good try, and I hope you did well. 2. Boolean algebra. So there he is on the top right. There's George Boole, an English mathematician. George Boole recognized that when we talk about logic and when we talk about sets, we're really talking about the same thing. Underlying both of these, it's the same mechanics that moves them both. And so he abstracted this idea. He said, okay, let's just make an abstract notation, what we have on the right here, that will sort of represent any statement in logic or sets. And in fact, we've looked at logic and we've looked at sets, but there are other situations where you suddenly realize that you're working in the same kind of system. Boolean algebra abstracts those ideas. The elements, the variables, are called ABC. The operations, we've got dot, plus, and prime. And the special elements, sort of the constants maybe, are 0 and 1. Using this Boolean algebra, here is the big theorem one more time. So take a look at this, pause if you'd like, and think about how all of these expressions work using the standard Boolean algebra. To my eye, this looks a little more mathematical, maybe because there's the 0 and the 1 in there, and we have the plus and the dot. But be careful, the plus and the dot aren't really addition and multiplication. Let me draw your attention to a couple of these in particular, the distributive property. So this one on the left, if I'm thinking of the dot as multiplication and the plus as addition, it makes sense. It looks familiar. A dot b plus c is a dot b plus a dot c. But the one on the right is weird because plus is not really addition. The dot is not really multiplication. We just call them plus and dot. I can distribute the plus across the dot. So a plus b dot c is a plus b dot a plus c. How we often use the distributive property is when simplifying expressions, and it's easy to miss that if you have this expression on the right, a plus b dot a plus c, that you can pull out the a, that you can simplify it to make the expression on the left, because it just looks so weird. It's not like any kind of arithmetic we've ever seen before. One other property I'll draw your attention to is absorption. This is a really nice simplifying trick also. And it's easy to miss, it's easy to forget because it's not like the kind of arithmetic we are familiar with. A dot a plus b just simplifies to simply a, and a plus a dot b, that simplifies to a. So keep an eye out for those as we go through problems and simplify these Boolean algebra expressions. Juxtaposition of symbols is the same as a dot, so very often we just write AB in place of a dot B. And we can see how this looks with De Morgan's laws. AB prime is the same as A prime plus B prime, and the quantity A plus B prime is A prime B prime. All right, some practice. Fill in the reason for each step. I encourage you to pause and to try this. You can look back at the properties and see which property is used for each equality. We'll do another one right after this, so if you just want to listen and see the reasons, you can do that too. Okay, give it a try if you would like. Here are the solutions. So what's happening in this first equality? It looks like the prime on the outside is coming inside the parentheses, but the dot is being changed into the plus. Next equality, the double prime disappears. Looks like that's the double negative. What about next? Symbols are just being moved around the plus because plus is commutative. Oh, here's the distributive property. So in that weird way that I talked about distributing addition across multiplication. And then a prime is 0, that's negation. And then the fact that b plus 0 is b, that is the identity property. All right, here's one that's a little bit longer, a little bit more involved, but I think you're up to it. Take a few minutes and see if you can identify the reasons for each step. All right, give it a try. And here are the solutions. Identity, commutative, negation, distributive. In this case, I've taken the quantity a plus b and distributed it across the plus. The next one is tricky, and this reason is absorption. So this whole expression, a dot a plus b, that got turned into a by the absorption property. Then distributive, commutative, negation, and identity. So in this case, we have proved that a plus b is equal to a plus a prime dot b. But this is a terrible way to prove that equality. There is a much easier way to do this. Can you prove that a plus a prime b equals a plus b with a much shorter proof? I think you can. Hint, use the distributive property. Give it a try. Okay, this final slide shows 3 problems, easy, medium, and challenging. We will look at these problems in class, and I will ask you to work with your classmates on giving proofs for these equalities. So you don't have to do them right now, but I encourage you, write them down and take some time with them, think about them, see if you can get any leads on proving that these are true. And then when we come together in class, you can share your work with your fellow students, and we will present them in class. All right, that finishes the section on Boolean algebra. I think this is really interesting. The fact that we worked with logic for a while and we worked with sets for a while, and then we kind of suddenly realized, oh my goodness, it's really the same thing underneath. Both of these are a Boolean algebra. We can represent truths in both systems using the Boolean algebra notation. All right, and this is a good place to stop.